Okay, so I'm going to switch gears a little bit and talk to you guys about green turtles, about coral trouts and oysters, and specifically can we monitor their physiology on a large-scale, cost-efficient way, and why something like this would be useful. I'd like to, before starting, acknowledge this is a work pretty much in the spirit of this whole workshop and of all the talks in this previous session across a number of organizations, including CSIRO, Deakin University, and especially CSIM and AIMS folks who are helping us to run a lot of these trials and make it possible. Okay, so let me start with the vision. So as I mentioned in my sort of segue, we are after sort of large-scale qualitative data on biodiversity and status of ecosystems. And we see physiology of animals as an interesting proxy that can deliver this information. So we're asking the question, is it possible to measure physiology and biology of key reef species in the marine environments, so directly in situ? So if you can imagine, you could actually collect data from your key reef species, indicator species. The question is, how is it useful? And so our thinking is, can we use this sort of information about, say, the behavior, activities of the animals, about, say, the feeding behavior and activities of the animals? Can we translate this information alongside the more typical data sources such as water quality data that's collected already on the reefs? Can we plug that into the large-scale models that people have of these ecosystems? And can we start answering questions around better understanding of the species? That's the obvious one. Can we better characterize the habitats? Can we look at the resilience of these organisms? Can we start quantifying industrial impacts on, say, the energetics of the animals or the well-being? But indirectly, can we also start looking at things like biodiversity or food chain composition in these ecosystems and start building baselines and long-term, so collect data over long-term on status and biodiversity of these environments. And then indirectly, in the third category, can we use these species as indicator species, sort of the canary in the coal mine approach, where they could provide us data on anomalies detected somewhere on the reef that are in contrast with, say, what the water quality model is telling us that should be happening on the reef. Okay, so how do we get there? So first, we need sensors. So we've looked at a few species. We've identified species based on how easy or simple it is to get the data out, and have a range of 3 different species. So we've looked at green turtles at Ningaloo, designed a sensor that is designed in a way that can transmit data once it gets above water, so that's the nice part of it, and collect information about behavior and spatio-temporal characteristics of where the turtles are. On the right-hand side, we've got an implantable sensor that we use with coral trout. So we make a little incision on the fish, sort of the size of my forehead, pop the sensor in, and then that's got a probe at the end that goes close to the heart, and it's just measuring ECG signals. This was just a child playground accident, by the way. I'm not that dedicated to the science. And the fish didn't have to wait 4 hours in the emergency department either. And then finally, for the oysters, we're also looking at heart rate. We're also looking at gaping behavior, temperature, pressure of the species. So once you have your sensor and you collect this raw data, ECG, motion type data, gaping behavior, you need algorithms that will process this data. This is what my background is, and where this really comes from is it's challenging to get data from these organisms from in situ, from out on the reef, because of the complexities, lack of infrastructure, and so on. There are now methods to do it in a cost-efficient way, but they limit the amount of data that you can transmit over, with a low cost And so what this really means is the software needs to really become smarter on these devices. And so it needs to take the sort of high frequency data that you have no chance of getting out of the animals in situ, like 100 hertz ECG rates or motion rates. And then you have to run your machine learning AI algorithms directly on these little sensors over a significant period of time to convert them into feeding behavior or to classify the behavior that the fish is doing, to start looking at energetics and so on. And I'll show you a little bit later how we do that for the coral trouts. So once you have your algorithms, you've managed to compress these sort of large volume data into your information dense data. You need some sort of infrastructure that will collect the data at scale. So we have an example of that at Ningalu, which you'll see a bit later. That's our 3G gateway at Ningalu. And then after that, you need to sort of figure out how do you actually use this sort of data within the large-scale modeling frameworks, such as e-reefs that exist out there. So one of the challenges we'll be looking at is these models. They work typically on a different scale, spatial-temporal scale. They don't have as much resolution as the data that we can potentially collect with the fish or turtles. So we're going to have to solve the assimilation problem. How do you sort of reconcile the different spatial-temporal scales at which you're collecting the data? That's an example of the picture here from Macquarie Harbour in Tasmania. We didn't have an animal there. That was a starbug that was collecting dense data around oxygen levels. And you can see that the data measured actually on these devices can help improve the fidelity and the accuracy of the models. Another thing that needs to happen is how do we then bring these physiology models into the frameworks themselves? Can we have a virtual sort of oyster model that will give us sort of an expected physiological parameter anywhere on the reef, right? So can we take water quality models that will have an impact on the physiology, and can we augment some of the maps, for example, that Chris was mentioning in the talk today? Can we take these better maps that help us identify sites for the restoration, and can we augment that with expected physiology sort of parameters? Is the animal going to do well at that site or not well based on the water quality data? Okay, so just a quick rundown of the activities in the field. So we've done a trip to Ningalu earlier this year, put those little sensors on a couple of turtles. Now we had a sensor failure, so I can't show you really the data. We have only data from the beach. But what we did was we deployed this infrastructure for downloading the data, and we were able to show that sort of at a low cost you can target sort of large areas. So the numbers were probably about $5,000 installation of hardware on the land gave us a 300 square kilometers coverage of the reef. We are at the moment, as we speak, we are currently running a trial at CSIM in Townsville, where we have an implantable sensor that's measuring the ECG, through which we're going to get the heart rate, and it looks like respiration rate as well. It's measuring motion, depth and temperature, and so we're running these across 30 plus fish, across 6 different tanks, 3 different temperature treatments just to control for some of the impacts, so the temperature on the heart rate. And the goal is to basically try to detect when the fish is feeding and also estimate how much it's been feeding, so how much energy is coming in. And finally, we are building on top of SIRA projects funded through FRDC in Tasmania with oysters. The advantage of oysters is they are not moving, so they can have a surface profile to communicate data back, rather than the fish, which at the moment they're just relying on loggers. Okay, so just a little bit of data from the CSIM trial on the coral trout, just so that you see what sort of complexities we are dealing with these sort of low-cost sensors. So here is a 5-second picture of an ECG trace from a fish that we had to sacrifice because of infection. Can anyone see a heart rate signal in the graph? It's kind of tricky. The signals are very noisy, and from the algorithm's perspective, there are multiple physiological signals that are combined into the same time series. So these sharp spikes are actual heart rate signals, but you can see there are other signals there as well, which we sort of cross-correlated with a video, and it turns out that this is related to respiratory, to the breathing of the fish. So any sort of muscle activity will have a voltage impact on the ECG sensor, which is a tricky thing from the algorithm's perspective, but we're also excited because the sensor is actually providing different physiological signals that we can work with. Once you sort of figure out your algorithms and are able to detect the heart rate, you can then start looking at the animal in sort of a longer time frame. And so this is the same fish that is about a 3 weeks period of time, just looking at the heart rate. Now the algorithm is still a bit noisy. We haven't really figured out how to accurately get the heart rate, but you get a sort of rough picture. So for about the first week until the June 5th, that was the period of the surgery at the beginning and then the recovery of the fish afterwards. So we didn't feed the fish so that we protected. And then you can see a couple of spikes in the heart rate. Okay, so, let me talk first about the big spike at the end. So the heart rate of the fish is actually depending on the temperature. It roughly increases, it roughly doubles every 5 to 6 degrees. So that's something we have to control for, and for this specific fish, we increase the temperature in the tank in that period of time from 24 degrees to 29, which roughly doubled the heart rate. But in those periods before that, the fish went through a couple of feeding trials where you could see the heart rate actually, and the video is playing one of the feeding trials, where you could see a short spike in heart rate, which is really quick, and then a slow tail as it's coming down as the fish is digesting the food. Since the temperature of the fish is the same as the water, they increase their metabolism by increasing the heart rate. So that's how we can then detect when the fish is feeding, hopefully distinguish that from other activities, and from the length of the tail, get an estimation of how much the fish has actually eaten, and over time to get to the energetics model as well. Okay, I'm gonna skip over the performance. Basically, this is about the radio communications interface, and at low cost you can achieve sort of large scale or workable scales on the reefs. So just in summary, reef restoration and failure will need a careful assessment on both quantitative and qualitative levels. There's a lot of work that's happening in this space. Where we're coming in is we're trying to sort of think outside of the box and see whether we can start getting qualitative data on the health and the biodiversity of these ecosystems. The same data will help us potentially improve the large-scale models. And finally, if you target indicator species, the same data can help you detect anomalies in pollution, in industrial impacts and stuff like that, say in the restoration projects. All right, so I'll just leave you with the acknowledgements for the funding, and again, just mention this has been a nice collaboration between 3 different organizations, and also within CSIRO across different business units, and a lot of people work hard for all of this data to come together and potentially, hopefully, give us good results. All right, thanks.